Okay. So we have the pleasure to have back Nathan Kutz. That is very early morning in Seattle, Washington State. And I hope to be able to visit personally another time. I don't know, future traveling are so complicated, even to go back to Italy. So Nathan, please, a lot of people have loved your first lecture, so we're very much looking forward for the second one. Please, Nathan.
Okay, hi, good morning, everyone. I hope you guys had a nice weekend, and so we'll continue on with where we left off. And what I want to especially talk about in this set of lectures is neural nets. So in fact, I've broken up today's lecture into two pieces. One is to talk about how we want to use neural nets in all of this data-driven discovery methods and data-driven modeling. And then what we'll do is the second half of this is talk about some practicalities about sensors and sensor measurements and the limitedness of some of your data. So that's what I wanted to kind of finish off with these workshop lectures on. So I have a quote here that you can see. It's by Stefan Malat, this is the first sentence of his paper. And Stefan Malat, I think, is just one of the absolute best people in the world today in math and working also on some of these data-driven problems. And one of the things I want to emphasize here is that he says it right there. Supervised learning is a high-dimensional interpolation problem. Now, we talked about Kepler versus Newton last time, and a lot of what we want to think about is extrapolation. And there's really what we think about often in engineering and physics is you build a model for a system so that you can extrapolate to new regimes. But neural nets are supervised learning, and fundamentally they're interpolation. And so using them in targeted ways becomes very important, and not getting too caught up in what they can do, right? They are interpolators, and just have that in mind always. All right. So let's start off back to this picture. This is one of the first pictures I gave last lecture, which is we want to think about taking data, and there's two key pieces to doing discovery. There's coordinates and the dynamics. So again, part of what we're looking at here is this structure where you use the neural net to discover a set of coordinates, and then in the dynamic layer, you can use different methods like this building a linear model or building one of these sparse identification models, these not SINDY models that we talked about last time. And so this is what we're going to follow up today on is how do we use neural nets to our advantage? Okay, so neural nets are being used everywhere. And there's very much a temptation just to kind of throw your data in the neural net, see what comes out, and claim success. And I see this often throughout the engineering sciences. You take a bunch of data and you do these things. And there's different kinds of ways to build neural networks. There's a lot of different architectures. And in fact, here's just some of the very different architectures that can be constructed that have different design principles and can be useful in different scenarios. And so one of the questions we can ask is, what's going to be the useful scenario for us doing engineering sciences, especially in terms of model building? And so that's what I want to get after here. And part of what I want to start talking about is this idea of using neural networks in autoencoder structures. So what an autoencoder is something like what you see here. You're going from an input space to a new space. Let's call your input X, that's your state variable X, and you're going to make a coordinate transformation to a new variable Y. And all this encoder does is it learns some nonlinear map from your original parameter space where you collected the data to this new parameter space, which you're going to learn through training. And the question is, what do you want to have happen inside of this coordinate? Okay, so this is work with Bethany Lush. There she is. She finished her PhD back in 2018, and she's now at Argonne National Labs. And she's just fantastic. She really kicked off a lot of really interesting work for the group here. And a lot of people have followed up from Bethany's work since. And so here's the idea. I want to learn a coordinate transformation, and that's exactly what I'm going to use the neural network for, to a new variable, and then back out. So I want to be able to come back to my original state space measurement space. Okay, so that's the decoder. That's that pink one on the right. And then the question is, well, what do you want to have happen in this new variable, this y of k? Well, let's start off with something simple. How about, can I learn a mapping so that when I move to this new coordinate, the dynamics are linear? This is exactly what dynamic mode decomposition and Koopman theory tells you, is you can make a transformation where the dynamics becomes linear. And so the idea here is to use the neural network to learn a coordinate transformation for which this is true. So if you look at the bottom left picture there, the neural net, you go from x of k to y sub k, and y sub k plus 1 is 1 delta t into the future, and you want to move into the future with some linear map, some linear operator. And also notice that it pinched the encoder structure pinches the dimension down. So I want the dimension of the dynamics to be as small as possible. In other words, to be at the intrinsic rank of the dynamics of the actual system. So that's what I'm trying to do in building this neural network. All right, so here's an experiment to try. Let's take the pendulum. A lot of people think the pendulum is easy. You know, we say, oh, look, a pendulum, isn't that completely known? Well, the linear pendulum is completely known, but that's an approximation for small amplitude oscillations. When you have large amplitude oscillations, your governing equations, right, are that theta double dot equals sine theta. And so it's a nonlinear, fully nonlinear dynamical system. And interestingly enough, when we try to take that pendulum and linearize it, we fail. That's like the simplest dynamical system. And I just told you, let's try to find a coordinate embedding to make this work. And the first thing that happens is you fail. So the question is, why do we fail? And it took us a long time to figure this out, even though after we figured it out, it was so obvious why we failed. And it's just simply due to the fact that this problem, and like many like it, have a continuous spectrum. What do I mean by that? Let's go to the Duffing Oscillator. And this is where I pulled out my notes from graduate school. So I even just scanned them here just to show you that these are like my handwritten notes. And this is a problem I was doing in asymptotics and perturbation, which was this Poincaré-Lindstedt to a pendulum which has a cubic perturbation to it. So this is the first correction to the sign of the pendulum. And you ask the question, what does the cubic do to the dynamics of the pendulum? Well, two things happen generically with nonlinearities. One, nonlinearity shifts the frequencies, and number two, it generates harmonics. So in other words, if you look below there, that is the asymptotic solution for epsilon being small. And so you notice your sign, which is the oscillation, gets shifted by epsilon in frequency. Okay? So in other words, the nonlinearity starts to shift the pendulum frequency, and the correction term that you have there has a sine of 3 of the angle, sine 3 omega. So it starts to generate sidebands or frequency content. That's harmonics of the initial frequency. One way to look at it is in the spectrogram. So what you're seeing here is that really bright bottom one is on the y-axis is the frequency, on the x-axis is the strength of the perturbation. And notice that as this perturbation gets stronger, notice the frequency shifts. Notice that there's a 3 omega, and you can see a 5 omega. There's a 7 omega. So what you do is you generate harmonics and you shift frequencies. So if you're going to try to represent this, notice that you have to represent all these frequencies within a single model. So in other words, it has a continuous spectra. And so it's very hard to do in an autoencoder, which wants to find a little linear model, but it has to be able to handle all these frequencies, and it can't. So we fix this problem by just simply modifying the network structure. And a lot of times, just modifying your neural network structure is really the critical piece to making all of this kind of come together. So what we did is, in addition to learning this autoencoder structure, we also learned how to parameterize the linear model we want. In other words, it's not just a linear operator that takes me from one point in time to another point in time. It's a linear model that has a parametric dependency upon the frequency. And this allows you then to keep the 2 degree of freedom system that you know that pendulum is, right? It's theta, theta dot. You can write that, that's your pendulum equations, right? Is you can write it down as a 2 by 2 system. That's the intrinsic rank of the pendulum. And that's what I want my model to have as the intrinsic rank. As long as I parameterize the frequency, I can do it. So here's the training of the neural network, and these are the different loss functions, and we just do this in TensorFlow. And TensorFlow is nice because you just put Python on your computer. You can download it for free. You can download TensorFlow trivially, and you can start programming neural nets. And so here are some of the loss functions you can do. And so what can we do with the pendulum? Well, on the left panel there is the dynamics of the pendulum. On the top is its phase space, right? It's theta versus theta dot. And so what these are these closed nonlinear oscillations that you get when all the way up to the saddle, right? All the way up till it's almost in the upright position. Below there on the left is the nonlinear oscillations. You can see they start to get to be strongly nonlinear oscillations. They're not sines and cosines anymore. They're a little bit more exotic. Okay? And the question is, can you take a system like this and linearize and make that pendulum linear all the way up to when it's in the upright position? And the answer is yes. And in fact, what you're seeing in these set of charts there in the middle is at the bottom, you take this phase plane, and in this new coordinate system, it turns into a circle. And in that circle, you have a matrix A that tells you, a linear operator that just tells you how the pendulum is evolving all the way out. Even when it's very strongly nonlinear, you have a linear model for it. And the eigenfunctions, let's say the nonlinear eigenfunctions that do that for you, are there on the left. This is your transformation into this space that linearizes the pendulum. We can do harder problems in pendulums.
May I ask a question?
Yes.
This is the conservative case.
Yeah.
For the dissipative case, things change?
Yeah, but you could still learn basically a linear model whose eigenvalues no longer going to be complex conjugate pairs. Now you'll have, as you look at that 2 by 2 system, what you'll find is 2 complex conjugate pairs with a real part that has a negative real part. So a damping. So you can learn a linear model even if you have the damping.
Going one step ahead, and if I include a barrier, a pendulum with a barrier, so that you have shocks in the dynamics, do you believe it's still possible?
So we have linearized things like the Burger's equation that has shocks. Yeah, so you can linearize quite a few things. In fact, I won't talk about it so much here, but even something like the Kuramoto-Shibashinsky equation, which is a very strong nonlinear spatial temporal system that's with chaos, we can linearize that whole thing. Actually, I was a little surprised we did it, to be honest. It's kind of amazing. I didn't think we would be able to do that equation. And what really it relied on is having a very large diversity of initial training data. And we were able to take the Kuramoto-Shibashinsky and map it to a coordinate system where the dynamics was linear. It's kind of unbelievable, actually.
Very impressive.
And that's actually some of the amazing power of neural nets is that some of the things you can do with it, some of the transformations that it can learn because it's their nonlinear transformations, it's really impressive what can be done.
Mm-hmm.
So that's the pendulum. Here's flow around the cylinder. So flow around the cylinder, this is when you have von Karman vortex shedding. And again, this is a nonlinear oscillations that describe sort of the shedding of the vortices. And what you can do is take this dynamics and take the reduced dynamics of this system. In other words, if you look in a low dimensional subspace, and I talked about this example last lecture, but you can take this thing, which was a nonlinear dynamical system, and you can linearize it completely. And there are the eigenfunctions on the bottom. And so this is, again, a little harder problem, but it shows you the concept of taking data, finding a coordinate system, and the coordinate system we want is we'd like to make linear dynamics happen. Okay, so what you're seeing here is this ability to say, take a neural net and allow the neural net to do all the heavy lifting of finding you this coordinate system. What we typically have done in the past is we prescribe the coordinate transformation, right? We write it down. Or we use things like Fourier modes or wavelets, right? So all these prescribed transformations we have, and what this does is says, I will just learn a nonlinear mapping for you. And the compositional nature of a neural net allows for an incredibly flexible architecture for learning very sophisticated coordinate transformations. But with that said, learning a linear model, I mean, linear models are great, right? Because we can solve them very nicely, but it's a very harsh constraint to learn a linear model. So what we're going to do is relax this Koopman constraint, in other words, the constraint of a linear model, and allow ourselves to learn a nonlinear model in the middle. So find a coordinate transformation and learn some nonlinear model. Okay, and now we're going to tie together what I had talked about in the first set of lectures with these neural networks. We're going to come back to dynamical systems. And here you go, dx dt equals f. And what we did with this SINDY algorithm, right, is you, from the data, can you learn some parsimonious model? And remember, one of the things I talked about was that sparsity was really a critical component of this, of the regularization you want to apply to get a model out. And so we're going to bring that same concept here, but now start thinking about it in terms of neural networks. Okay, so again, SINDY is there. You're going to take something like the Lorenz equation. Here's your basic model, and then you can back this out. And the way this happens, right, let me just remind you, is that you take your system and you have data. Now, suppose you don't actually know the governing equations. I just give you time series of x1, x2, x3. Well, the first thing you do, again, is you can compute their derivatives in time. So you have x1 dot, x2 dot, x3 dot. So this is going to be the vector b in ax equal to b. And then you make a library of potential terms. Like, well, what could the dx dt be? It's some f. Well, what is f? Well, I make a whole library. I make a library of all kinds of candidate functions. And that's the matrix A. So now I have ax equal to b because f of x is equal to x dot. And I computed the x dot, that's the right-hand side. The f of x is the libraries plus a set of their coefficients of the library terms. And what we talked about last time is that what SINDY does, it promotes sparsity. How few of those library terms of potential functions do I need to describe that data? And when you do that regression, what it pulls out for you, it discovers your governing equations. So that's what's nice about SINDY, is it just goes and finds you a model. Of course, there's caveats. There is noise that can affect your ability to do this, multiscale physics, all kinds of things. And I addressed some of them in the last lecture, but we've been working very hard since this original paper to overcome many of these obstacles. So again, once you've done this, You didn't know what the governing equations were. You now have an identified system, and it turns out you actually got back the system you started with. Okay, that's SINDY. So the question is, sorry, let me come back to here. So I showed this how to demonstrate this in practice last time. It's this really kind of flexible architecture just built on AX equals B. And now we're going to go and actually talk about real data collection. So you say, okay, this seems to work. There's a couple big assumptions. One assumption you're making is your measurement is X itself, like the state space. You actually know what the state space is. Well, in a lot of systems, you don't even know what X is. So you got to figure out what X is. And let me give you an example. What if we just simply don't know the state space? Which means, what if we don't even know the right coordinates? That's kind of what I'm telling you. And what I mean by that is the following. Do you see that video there? And what do you see? You see a pendulum, right? And this is something we built here. We just attached the pendulum into a wall, bolted into a wall here, and then you can see the pendulum. But what I'm giving you is a video. Does the video know that there's a theta, theta dot? Right? I mean, you know this is a pendulum because you've seen it before. So you already know what the right coordinate system would be for that pendulum. But if I just give you video, then what is the right coordinate system? So I always think of this as the age of GoPro physics. I don't know if you, do you guys have GoPros down there? Those are those little cameras that they take and they go underwater and you do lots of sports and, I'm sure there's a lot of surfers and paragliders there in Rio that use these. But the idea is that like you just film physics. And the question is, okay, I filmed this thing, could I extract something meaningful even if I don't know the right coordinate systems? Same thing with this spiral wave on the right. This is what I measured, but I really want to understand what are the intrinsic variables for me to write down models with. Okay, so let's go do this. So what we're going to start off with is tying together this autoencoder structure with SINDY. We're going to bring these two together. In other words, SINDY relied on me having the right coordinate system, and I don't now. I'm just measuring some stuff, so I don't know what the right coordinate system is. But I have this SINDY model, right? Where the SINDY tells me how to discover, if I have the data, how to discover the governing equations. And then what I just showed you is neural nets are great at making coordinate transformations. So let's put the two together. So here's how it's going to work. I'm going to do an autoencoder. So I'm going to start with an input space. And what I want to do is make a transformation to what's called a latent space or the latent code. So this is going to be my actual variable I want to work with. I don't know what it is. In other words, think about the pendulum. The input space is pixels, the video of the pendulum. The latent code right there would be theta, theta dot. I don't know what the latent code is. The question is, can something like this learn it? And then I come back out. So I come in and I come out of this new variable. So my loss function that I'd pick up here when I'm training a neural net would be simply that the autoencoder, if I start at X and I come over here to X hat, they should be close. Okay. So there's my encoder. I'm going to build a neural network to do this operation for me. I'm going to train this neural network to learn how to map this. And then I'm going to figure out another one to get me back. Now notice that I have phi and phi versus phi and phi inverse. Making phi and phi inverse actually be its inverse is really hard. In other words, I just want phi and phi to be good approximations, but not exactly inverses of each other. That's a much harsher restriction. So that's my basic architecture. This is what I want to do. Now the question is, what do I want to have happen in the latent variable space? In other words, once I'm in Z, what do I want to happen? Notice this is almost exactly what I just did with linearization. And what I said I wanted to happen in Z is I wanted a linear model. But now I say, well, I don't need a linear model there. I want to do maybe something a little bit different than a linear model. In fact, I want a SINDY model there. So we connect all this up. And now, what do we do in the middle? We're going to do SINDY. So once I'm in this latent variable space, I'm going to go in that space, and it's color-coded. I'm going to apply the SINDY loss function in the middle. In other words, find me a coordinate transformation so that when I get this dynamics out, it is sparse. It is a parsimonious representation of a dynamical system. I'm finding a coordinate that goes with sparse dynamics. Okay, that's going to be the goal of bringing these two methods together. The loss function for SINDY is given right there. It's a sparse regression framework that we have been playing around with. Okay, so that's what I'm going to put in the middle. And so now I start cooking up some things. So first of all, let's talk about this variable z, this latent variable, and its connection back to the original variable x. So what just showed up there, you can see it just popped up right on the bottom under z dot there. This is the connection between x and z. So x and z are going through the mapping phi. So if you want to get z dot in terms of x dot, there's a gradient computation that's made there across that neural network. Now it's going to turn out to be important for us. Okay, and then this is phi represented in the variable x. And then so what we can do is add these together to create a loss function. And the loss function has the autoencoded portion, which is come into this coordinate system, come back out with a loss function. And then in this new variable, do the SINDY regression. But notice I framed the SINDY regression in terms of the x variable, not in terms of z. And of course, you could ask the question, why did I do that? And here's why. It turns out one of the interesting things about neural networks is they break in a lot of interesting ways. So when we first trained this, we trained z to have just the SINDY loss function. And what it did is said, oh, you want to satisfy something here in z. So what it did, the neural network got smart, and it said, all right, tell you what, when I go from x to z, it's almost like it decided I'll just divide by some big number, like 10,000. So when I'm in z, everything's tiny. So whatever loss function you propose in z, it's like automatically satisfied. So like I could divide by 10,000 coming in, and then multiply by 10,000 coming out, and then I have this loss function for z, but since z is so small, it's like essentially you satisfy the loss function, because z is almost 0. And so instead, we satisfy the SINDY constraint in x, and it can't cheat on x. It can't say, let's make x small. X is what it is. So these are the kind of things that happen when you train neural nets. They always do things that after the fact, they are obvious, but during the training process, you get very frustrated. In fact, if for those of you who decide to train neural nets, I need to prepare you. You need to be prepared to fail a lot. Like when you do a neural network, you think you have the right idea, you put it in there, and none of it works. And you wonder why it doesn't work. It should work. And a lot of times when it doesn't work, it gives you no clue of why it's not working. And so you try new things and you still don't know why it's not working or working. And then eventually, after a very long time, you figure some of it out and you get it to work. This is exactly what happened with us with this project, with Bethany's project. It was months and months and months of failure before we got it to work. So I'm just preparing you. Don't think that just throw it in a neural net, it'll work. No, it won't. You're going to fail, and you'll keep failing, and you'll fail some more. I've never failed as much as when I've done neural nets. But when you finally figure out how to get them the right loss functions to make them work, it's all of a sudden, oh, now it works perfectly. As if you never failed. Anyway, just preparing you for that. So don't be discouraged if you find yourself failing a lot with neural nets. All right, So the last piece of loss function, you see that just got added there on the bottom right is blinking there. We also add an L1 penalty to the loading C. In other words, to make sure we sparsify this. Because, you know, before we were doing sequential thresholding to sparsify the solution, and now we just impose an L1 penalty on the norm of C. Okay.
Nathan,
Yes.
may I ask a question? Another question.
Yeah.
Regarding a comment about the failure of the training, what I can imagine that you have some degrees of freedom to play during the training, the configuration of the neural net, how many layers you're going to insert, the coefficients of the penalty terms. But in the end, I imagine it's a trial and error game. Or is it possible to be smarter than this?
It's always looks possible to be smart after you figured it out, like everything else. During the time, you know, after the fact, it is true that after the fact, it's obvious why we failed in many of these cases. But it wasn't obvious at all when we were trying it. So I don't know if I have any good advice there, except for as you get experience and you start seeing how, because the neural network has an amazing flexibility. So it actually does things that you don't expect. And you have to really figure out, even though you know what you want it to do, what you said mathematically allows it infinite variety of solutions to what you want. And it'll pick some of these and you're like, why is it doing that? Can it figure out that this is obviously what I mean? And so I wish I could say that, in fact, we learned some valuable lessons, we can write them down, and so now you're set to not make these mistakes. But every time we seem to train neural nets, we're right back at failing. The nice thing, I think, what we've been able to do is diagnose our failures more quickly. And so that comes with just experience.
So the main ingredient is try and get experience.
Try, get experience, try new things. Nothing's gonna break. I mean, just try it. If it fails, you try new stuff. Like, right, that's the nice thing, is like, you shouldn't be scared to play around with this. Who cares? It's just some Python code and TensorFlow, and you just an optimization with lots of local minima everywhere. And, you know, just try stuff. See what works. You're gonna have a lot of failures. Who cares? Try some new stuff. And eventually you'll start figuring some stuff out. But there's a lot of stuff that's non-obvious that happens in the failures modes that are important for you to just be aware of.
Mm-hmm.
Okay, so there is our loss functions. And after the fact, it seems so easy. How could we ever gone wrong, right? Except for we did for quite a while. And here is one of the failure points that at least I discussed a little bit. Notice how I formulated this, which is...
Please, just a second, just to interrupt you, but may I ask a question about this formulation?
Yeah.
Regarding to the second term, it seems that this derivative of z dot is quite sensible to the Jacobian matrix of phi.
Yeah.
And this is based, this loss function is based on the x dots. And what about when you have a lot of noise in the data sets? What's happen with this second component of the loss function?
Oh, that's always a problem if you have noise, right? So we can handle some noise, and we've actually even figured out ways to denoise these with using neural nets as well. So, so yeah, so obviously the gradient is there. I mean, in either case, either way you're computing z dot or you're computing that gradient, noise really compromises your ability to produce good derivatives. So normally the way you do derivatives, we do it through total variation. So you would never do finite differences with derivatives. They'll be awful. But if you do total variation, you get a little bit smoother derivative and you have a better shot.
But what about your experience with this? You can use some filters to deal with that. You can smooth this noise and work with this, or
Yeah,
is always will be a problem for?
Well, total variation is like smoothing in some sense. And so we just have been using that. And then more recently, we've been doing instead of filtering, we learn a noise model itself. So what I mean by that is the following. One of the things that we did with the neural net was we said the following. Suppose I have time series data, and suppose I believe that that time series data is, that measurement data is noise plus some deterministic system, right? So I have some deterministic system with noise on it. And then the question is, how could I separate the deterministic system from the noise? And so what we said is, well, a deterministic system, if I gave it to you, some nonlinear system, you might throw it into something like Runge-Kutta, like OD45. And so, you know, there's time stepping constraints that we built for solving differential equations. And so one of the things we did is said, how about this? Let's take the data, randomly split it, and ask the following question. Can we, with the random split, and so we start iterating, can we find the portion of the signal that satisfies a Runge-Kutta step over many time steps, and the stuff that doesn't satisfy Runge-Kutta? The stuff that satisfies Runge-Kutta is your signal. The stuff that doesn't is your noise. And so it learns how to separate signal from noise this way fairly robustly, and then it allows us to handle actually significant more data noise than just standard methods.
Okay, thanks. This looks like a wavelet decomposition. So
yeah,
that's great. Okay.
So by the way, one of the failure points here, notice that going to that second loss function, I impose a SINDY loss in the X variable. Why not just do it in the Z variable? Because if you do it in the Z variable, the neural network cheats. What it does is says, okay, see the loss function there? I have 3 terms I got to minimize. So all it did is said, tell you what, and I already highlighted this, when I go through the transformation, just make Z super small, which means the loss function too is automatically satisfied, which means I can ignore it. So it does. And so it doesn't even do it doesn't do any model discovery because it just says Z is small, let's throw it away. So that's why you need to write it in terms of the X variable, right? And so that's part of what we've done is we've said we can actually write this in terms of Z or X or put them both in. So there you go, that's the new loss function. And those are the kind of tricks you have to figure out when you go through this thing, which become actually really critically important. So a couple comments with L1 doesn't give you something that's perfectly, it gives you a lot of small, L1 just promotes a lot of terms that get very small. And then at some point we threshold them out. And so now that's kind of this loss function. Now let me give you an example. So here's what I'm going to do, just to show you how it works. I'm going to take the Lorenz problem, and that's on the left. And for each one of the Z1, Z2, Z3, I'm going to glue to it some spatial mode. Okay? So I'm going to pick some 3 different spatial modes and say that each mode is evolving according, its amplitude is evolving according to Z1, Z2, Z3. So what you end up getting is some structure like you see there in space-time. So now what I've done is I've hidden the coordinates from you. What you have is that data, spatial temporal data. You don't even know that there exists a Z1, Z2, Z3, or that there's a coordinate transformation that could get you there. Because it's actually, in fact, a nonlinear transformation that we made to get to this new coordinate. So the question is, from the data, could I discover the nonlinear coordinate transformation that we put on there and discover the underlying governing equations? So here's what we actually find. So here's the actual dynamics. So this is the actual Lorenz model, and this is our discovered model. And the discovered model, interestingly enough, is a linear transformation away from the actual model. So this is kind of interesting. So even though you buried this dynamics inside of a spatial coordinate system nonlinear transformation, it was able to undo that nonlinear transformation and discover not only the underlying dynamics, but its dimensionality as well. So this is very encouraging because what it allows you to start thinking about doing is that from this scenario, this allows you to think about like, oh, I can go back to that pendulum, and if I just give you the video of the pendulum, it will discover theta theta dot from videos. In other words, from pixel space, it will discover theta theta dot and then discover that theta double dot is equal to sine theta. In other words, it does all the work for me of discovering a coordinate system and governing equations together. We would love to apply this to actually the data that Kepler had, right? Take Kepler's data, and could you discover, in fact, coordinate system is the heliocentric world, and F equals ma. That's what you need, right? You need, those are the two key pieces that transform celestial mechanics. F equals ma and heliocentric model of the universe, geometry or coordinate system. This does both at the same time. In fact, the only way to get a parsimonious model is if you are in the heliocentric coordinate system. The Ptolemaic system requires you to have all of these corrections to get the right predictor, because you need lots of circles on circles to be able to make your predictions. Let me just, oh, I'm gonna stop share. Okay, oh, come on, I'm gonna try to stop share. Oh, okay, oh, here we go, there we go. Can you guys, what are you guys seeing right now from my screen? Oh, here we go. Let me just share my other screen here. Boom. All right, I'm gonna move over to these here because I want to finish off some slides here. Okay, so this was the idea, right? This is the work with Kathleen Champion. So Kathleen did this work. So the whole point here is to discover this pairing. Find me coordinates, then give me governing equations in these coordinates. And part of the reason I like what Kathleen did so much is that this right here is what we have done throughout our history of scientific discovery. And what you're allowing the neural network to do is to automate this process to help you discover this pairing of the two. And I already showed you this, but the bottom one is exactly the pendulum. The pendulum is the one that's kind of a really cool example, right? Because I could film the pendulum and from the video itself, learn that there is an intrinsic coordinate system, which is theta theta dot, and then learn the right governing equations in that coordinate system. Okay, couple comments that I wanted to make here. And this regards the idea of what do we really learn from this? Well, the neural network learned a coordinate transformation, and that coordinate transformation is not generalizable. It's very specific. So if I give you a video of a pendulum with a certain length pendulum, it can only learn a transformation for that exact length pendulum. If I take a pendulum and make it twice as long, that neural net, that coordinate transformation is no longer valid. It doesn't work at all. However, the middle part, the SINDY layer, where you learn theta dot is equal to sine theta, that's like a universal truth, right? That's my governing equation for the pendulum that holds for all pendulums. So F equals ma, for instance, is the universal truth that holds across all of physics. But for every single system, you have to set up the geometry again. Okay, so I want to do F equals ma for Mars, which is different than for Venus. If I do F equals ma for me throwing a heavy ball versus a light ball, I have to get the right coordinate system for each, even though the F equals ma is the same for all of them. So I just want to make sure I highlight that here, that the middle layer where you learn the dynamics is generalizable. That's where your extrapolatory thinking can come in, whereas the neural network itself is purely interpolary. It cannot do anything except interpolate the data you gave it. Okay. So I'm going to continue with this idea of what neural nets can do for us before we move on to sensors and just give you a highlight of some other ideas.
Nathan,
Yes.
may I ask a question in that last slide? Well, the coordinate choice it's very particular to your problem. But in some sense, you're using a black box tool to try to discover the right coordinate system here. So if you have some previous information about the system, may be helpful to include, so that you know that you don't know exactly what coordinate system is, but you know that it's cylindrical or better than Cartesian coordinates because you have some kind of curvature. How to include this kind of prior information in this framework?
Yeah, that's a great question. So, in fact, there's a lot of this, machine learning. That's one of the big things that people are pushing on right now is physics-informed neural networks. This is George Karniadakis at Brown has a big effort here. We have some effort there. And the idea is, so for instance, suppose you know things like I have radial coordinates. I have certain symmetries. I have things that I know about my physics system that help you understand the physics. How do you put them in to this system? So neural nets aren't often as easy to work with this way, right? Because it's not clear exactly how you would impose structure on just an autoencoder. But that's exactly where people are trying to work now, is to try to figure out, are there ways to impose symmetries or structure on these neural networks that enforce known physics constraints? So absolutely. So that's sort of I would say that's an area of a lot of modern research. And I would say that generically, the answer should always be the more physics you know, the more you should impose.
So pins are the answer for here.
Yeah.
So physics informed neural nets.
Yeah.
Mm-hmm.
Yeah.
Thank you.
Mm-hmm. So let me move on to one other issue here, which is how else could you use neural nets? Well, I'm going to tell you about, so notice that we've been using neural nets to discover coordinate transformations, right? So spatial structures and transforming them to a new variable in space. I want to instead say, well, we could just use this whole neural net on time coordinates instead. So, one of the things that all of us want to do is do forecasting. That's one of the biggest things and biggest challenges. How do you do a good job forecasting? Because extrapolation in time is really difficult, right? That's just, and part of what we want to do when we extrapolate in time or forecast in time is try to get a good as prediction as possible for as long as possible, okay? So here's what we were doing with Henning Lange. There's Henning right there, postdoc working with me. And we were just basically saying, well, one of the great tools that we've had in the past is Fourier to forecast. In other words, just do a Fourier decomposition of a signal and you get some interesting information. Now, the problem with Fourier, however, often is that what if your signal is not periodic on a domain, or you only have part of a signal, or you have sharp signals like I'm showing you here, which require you to have lots of Fourier modes because it's broadband. What then? So what we started to think about is, all right, what we can start doing is start understanding how to do some regression frameworks and then tie it into neural nets. So a standard Fourier trick might be to take a signal and basically represent it as a sum. In other words, set this up as a minimization, as find a set of Fourier modes, and here are the Fourier modes, where instead of when you do a Fourier transform, the frequencies you get out of the Fourier transform are prescribed by the domain size. Here, what you do is you learn a set of frequencies that you need, a minimal set of frequencies you need to represent a signal, to represent the some signal x of t. But part of the problem is when you go to signals like this, where it has very sharp structures, if you look at the Fourier transform of that, they'll start to look like a delta function. So it's looking broadband. So this Fourier decomposition, you're going to need a ton of modes. But if you look at it, it still looks pretty simple. It just looks like something oscillating. It's just that it's not your standard just Fourier transform. So instead, what you could do is say, how about if I learn a map? So this is what we're going to do, is we're going to put now a neural network here, and the neural network is going to take this information here and say, how about if we transform this into, make the time series, find a transform that makes it look more sinusoidal. So that's what this thing does. It's a neural network that takes signals like this and tries to make them as sinusoidal as possible. And in that coordinate system now, is very easy to represent them in terms of a small number of Fourier modes. All right, that's the goal. And by the way, here's the thing I want to highlight. Fourier modes are highly interpretable. And we're using this neural net in a very targeted way. And one of the things I want to highlight to you is that, you know, there's a lot of talk these days about just throwing time series data into a neural network, and neural networks are going to beat everything. And that's just simply not true. And we took some power grid data, and power grid data is interesting. It's sort of stochastically varying, but sort of has some periodic structure, a little bit different spatial, so temporal frequencies in there. And we asked the question, how well can we forecast using this kind of methodology? Well, this Koopman forecast, where we learn this coordinate transformation, just beats everything, especially for long-range forecasting. And in particular, it destroys the performance of LSTM, GRU networks, echo state, RNNs. Like, we took all the state-of-the-art methods along with ARIMA methods and things of this nature. And you can see the performance here is significantly better, especially for forecasting horizons that are out in the future a ways. LSTMs and all these neural network structures are really good at predicting delta t into the future. And what this is telling you is that Koopman can predict many delta t's into the future much better. And so that's a really powerful thing. And all you did is used a little bit of a targeted neural net to make a coordinate transformation so that Fourier modes would work better. You can also use this for doing things like reduced order models. So on the top, what you're seeing is this high resolution PDE simulation of a cavity flow. And this is often one of the examples people give in reduced order models. And you see this thing circulating, and that's a big PDE you're solving, yet it has some low dimensional structure with some time series data that's kind of complex. And the bottom, you simply take the time, you just take an SVD of the data, look at the time series, do this data, do this projective, learn this Koopman forecasting, and what you're doing there is just, fit it to a bunch of Fourier modes in this transform space, and it's almost perfect. You're not even solving a PDE anymore. You're just saying, here's your projection to the future. And it totally nails it. It's pretty impressive for quite a long ways out. A couple more thoughts, and then we'll go to a little break. You can also think about multiscale physics systems. This is about training neural networks that have hierarchical architectures where you learn coarse-grained features and then you refine them where you need, much like you would with multi-grid. This exploits transfer learning and multi-grid methods together in a neural network architecture structure. This is what my student Lulin. And then also you can do boundary value problems. So you can take this whole thing, instead of being time-dependent problems, you can make them just boundary value problems. And this whole structure holds up there, where you can learn in embedding to learn governing equations for boundary value problems. And even more recently, and this will probably be up in the archive in the next couple of weeks, we can take a nonlinear boundary value problem, learn a coordinate transformation to make it linear, and then we can get the Green's function. That's the fundamental solution. So now you have a way to find essentially Green's functions for nonlinear boundary value problems by using this coordinate transformation. I'll stop there, take questions, and let's take a 5-minute break.
I have just one question. when you talk about the double pendulum example, the linearization is global, or is a match, or is a set of local match transformation? They are matched. They are patched.
No, it's a global transformation all the way up to the saddle.
Okay.
And the big thing is that you have a parametrization of that globalization. That's the thing. Instead of a bunch of patches, you get a global thing with a one parameter in that model, that linear model.
Okay.
Yeah.
Thanks. Okay, so
other questions?
Let's see. We can take 5 minutes break and then we can see the question after, maybe.
Yeah. Okay. Let's take a 5-minute
yes,
break.
there is a question from Fabio Pereira. How about hyperband algorithm? Does it make neural network work?
Which algorithm?
Hyperband algorithm.
I don't know. Okay. Yeah, I can't answer that. I don't know if hyperband algorithm.
Okay, so let's take 5 minutes.
5 minutes. Great.
Okay. Have a good coffee.
Okay, it's right here. I got it fixed at my machine back. I'm ready.
Okay. Tem uma nova aluna aqui.
right.
New a cat student. Okay. So we can, that's the problem. So we can start back. Please, Nata.
Okay, ready to go. Okay. All right. For the last part of what I want to talk about is a little bit of the reality that we all face with the fact that if we're going to be doing data-driven modeling, a lot of what we often do, at least so far, we've been building synthetic toy data to just try these methods, and these methods are kind of diverse. They allow you to do different things. But when you get to real systems, the way you interact with the world is through sensors. And in fact, I think ultimately the data science revolution, it's all coming from sensors. I mean, presumably you guys all have these, some phones. My phone, I have a HD camera in the front and the back, right? I have, so I can bring in HD video off of a phone. These are sensors. We can buy laser pointers in Hong Kong for less than $1 a piece. Now, why is that important? Well, all these are the basis of sensors. And sensors is what we use to interrogate our world and pull in information and try to build measurements from them. Measurements were very hard to acquire for a very, very long time for humanity. You think about what Kepler really was able to do was Kepler was able to get Tycho Brahe's data. Tycho Brahe, he had a whole team in this castle up in Denmark to collect this data. He spent a lifetime collecting this data that we could do trivially today. But data has always been valuable, and it's always part of what we've used to build our theories and models. It's just that now with all the revolution we've had in sensor technologies, we can now acquire data almost instantaneously on almost in large diversity of areas and application areas. Some from PIV of measuring fluid flows to a whole brain imaging for neuroscience. I mean, it's really remarkable what the sensor revolution has done for us. And that's really what's driving this whole data science revolution, is just all of this amazing data we have available to us. But there's a question about how we're going to handle the data. And I want to start talking a little bit about the fact that oftentimes you have point measurements, and you have limited measurements, and you have noisy measurements, and how do you still make use of all of this to build models? And one of the things you've already seen me promoting sparsity in terms of AX equal to B, but randomized linear algebra is a technique that you might want to learn a little bit about. It's amazing stuff. So let's go into it. So I like this cartoon. I'll let you read it. So this is one of the rare instances where this pointy hair boss, I don't know if you guys know this cartoon Dilbert. So it was very, famous here in the US. But the pointy hair boss is usually an idiot. But in this case, he's actually right on. Notice where he says here in that panel, try using math. And Dilbert doesn't know how to do this, but in fact, we do know how to do this mathematically. And in fact, that's exactly what we want to do here, is something like estimate the entire ocean in how its temperature profile, taking only a small fraction of the data, 1%, maybe even less, right? And how would you take such small amount of data and estimate the entire global state of the ocean? And so what you really do need is you need math to do this. And so this, like I said, this was a funny cartoon because normally the pointy hair boss just is always an idiot and wrong. But in this case, you know, he doesn't know what he's talking about, but he does say try using math, and Dilbert doesn't know how to do it. So Dilbert needs to go back to school. He needs to take this mini course, and then he would be able to do it. Okay, so where do we get this idea of being able to take a small number of measurements and do a global reconstruction? And this really comes out of this idea of what's called compressive sensing. And compressive sensing was really big sort of around 2006, 7, and through 2010, 11. It was this idea of taking a small amount of measurements and doing a reconstruction based upon that. And how does this work? And the idea there was actually, in many ways, think about what a digital camera does. So a digital camera, when you take an image in pixel space, it's a huge pixel space. And the first thing you do is you take that image and you compress it like through something like a wavelet transform. And you look at the wavelet coefficients and then you throw away all the small ones. That's how you do image compression. You take images in, you put it in a basis wavelets where that image is highly compressible. And then you can ignore most of the wavelet coefficients and store the image at a fraction of the pixel space. Okay? So notice what you did then if you do that compression. You took this big picture and the first thing you do is you throw away most of the information in the compression process. What if instead, and this is the idea of compressive sensing, what if instead you just said, look, there's a small number of measurements. If I'm going to only keep 1%, what if I could just find out what 1% I needed to keep in the first place? And that's exactly what compressive sensing does. And again, all this is AX equal to B and promote a sparse solution. It's exactly what SINDY was. In fact, SINDY, we came to SINDY out of this. We were doing compressive sensing first and recognizing, oh, look, we know how to solve AX equal to B, promoting sparsity. What if, and then SINDY came out of this concept in many ways, understanding sparsity and how important it is. So the idea of the following, this is a cartoon by Richard Baruniak. Baruniak's fantastic. He wrote a really nice, like, little tutorial paper on this. And the idea is the following. I have a signal. What does it mean for a signal to be compressible? It means there's a basis in which it is compressible. Okay, so what you're looking at here, if you look at the top panel, let's call phi, or psi there. Psi is my basis. Let's say it's Fourier modes, wavelets. And what I know is I have a signal that can be compressed, or in other words, expressed in a small number of basis modes of that basis. So that's the vector A. The vector A is how much an image, let's say, is projected onto those wavelet modes, and most of it's 0 except for a few non-zero terms. So that's the idea of compression. Okay, so in other words, I have a signal that can be represented sparsely in some basis. And so you could say, like, oh, well then in that case, let's measure a system. That's what Y is. Y is a measurement of the system through some random measurement matrix phi onto the actual signal X, but X itself can be written as psi A. So ultimately, this just becomes, it's a linear algebra problem. You have some random measurements that are small number of them with an underlying signal that is actually compressible. All you really need to do is learn the non-zero coefficients of that matrix, which, so in other words, you solve AX equal to B, promote sparsity. That's compressive sensing in a nutshell. And what it tells you then is, so from a small number of measurements, I can tell you the non-zero elements, which means I was able to find the compressive information without actually taking the full thing and then compressing it. I just found those directly. I found the non-zero elements of my wavelets, of my Fourier modes, directly from this AX equal to B solve by promoting sparsity. That's it. So this is really fantastic stuff. I would say that this was super hot in 2006, 7, 8, 9, 10. I mean, everyone was like compressive sensing. Even Kendez and Tao wrote this paper called, compressive sensing, a universal encoding scheme. It was sort of really took off. But it's actually really hard to do in practice. So it turns out it didn't work as well as people had hoped. So I think that's the truth of the matter, is that mathematically it was great, but when you went to engineering systems, a little bit of noise, a little bit of real sensor measurements, and it doesn't really work that well. Okay, but the concept is really important, and that's what we're going to use here. There's also this concept of randomized linear algebra. By the way, all of these techniques I'm talking about rely on the fact that the underlying signal is low dimensional. So you take some high dimensional data, but underneath there is some low rank subspace where the signal and some coordinate system where everything matters. So in other words, the intrinsic rank is small in comparison to your very high dimensional measurement or state space. Randomized linear algebra also looks at this problem by saying, what I would like to do is I'd like to find this low rank subspace, but the data matrices I have are huge, and doing an SVD, the singular value decomposition to find the low rank subspace, is extremely expensive, or maybe can't even be done. So these randomized linear algebra algorithms, guess who bought them? Guess who took patents out or bought the patents from people? Google and Facebook. Why? Because their data is so big, and if they're looking for patterns in their data, especially around customers, then they can't even take the data and look at low rank features because they can't do an SVD on the data. However, randomized linear algebra allows you to randomly sample the data and construct much smaller matrices through a QR decomposition, and then basically project into this QR space, which gives you a much, much smaller dimensional matrix, which you do the SVD on, and then you have a pathway back through QR to the original high dimensional space. So this allows you to do matrix decompositions at scale. And again, it's relying on the fact that there's underlying sparsity in your, or low rank structure in your signal. Finally, I will mention the QR again. There's an entire body of work called GAPI methods. GAPI methods are basically, how do I subsample some spatial temporal data and reconstruct the entire state space? And there's a bunch of work on this in the reduced order modeling community because, again, there are low rank modes and structures that dominate the physics. And so once you have those modes, you can just massively subsample in this GAPI way and be able to reconstruct it. And one of the interesting methods to do this is this QR sensor selection. This is with Krithika Manohar. And all this does is takes your data and it looks to see which columns of the data have the highest variance, put sensors there. And so you arrange the data, that's how the QR is arranged, and it gives you the pivot points. In other words, QR pivoting tells you which points of the data have the maximal variance, and that's where it drops sensors for pulling out important features of the data. So all these are sort of centered around the idea of placing sensors. And so I want to highlight this by showing you a movie. So what you're seeing here is sea surface temperature data. And this is over, I believe, just over a 15-year period. 15, maybe 16-year period. And so what we've done with this is we've done this hierarchical decomposition of the data by looking at QR decompositions on fast, medium, and slow scales of time. And that's what this frequency window is. It's a little bit like a wavelet structure. And what we've done is ask the following question. I would like to measure the ocean. Oh, okay, come on. There we go. I want to measure the ocean, and I want to pick as few locations as possible and reconstruct all of the ocean. So you see where those dots are? Those are my measurement locations. And from those measurement locations, I can reconstruct the entire sea surface temperature data set. That's kind of remarkable because if you look at it, at any one time, I have no more than 4 or 5 of those balls on this map. And so what it's telling you is I can basically massively subsample this data and reconstruct the entire global temperature profile of the ocean with 4 or 5 measurements at any given time. And all it's doing is exploiting the fact that there's low rank structure in this data set. And by the way, this data set was, we got it from NASA. So this is publicly available data sets. And that's exactly what you want to start thinking about with sensors. How do you pick good sensor locations so you can do a task like this? How do you go about choosing these? And these are principled mathematical techniques that allow you to take data and understand where your measurements should be so that with a small number of measurements, you can actually reconstruct the entire state space. All right, so let's start talking about the mathematical framework for doing exactly this. And again, this is so important because in practice, you know, we can talk all we want about, oh, I want to do data-driven modeling. But the fact is, if you go to a real system with real data, it's limited, it's noisy, you've got issues that you have to deal with there. So I'm going to start talking about how to set this up. And here's the mathematical framework. So first of all, I have my state space X. And this is some n-dimensional system. And then I have measurements of that state space S. And I have P measurements. And generically here, what we're talking about is P is much less than M. Okay, so in other words, I have a few sensors and my state space can be very large. Okay? What do I want to do? I want to construct a mapping from my measurements S to reconstruct the state space, to estimate the state space X. So the mapping is given right there. X hat, which is my approximation to the state space, is just some map F from the sensors S. Okay? And the optimization is very trivial to write down. There it is. I want to find F such that if I look at the data, each of the n data points, right? I have some training data. I want to learn an F so that if I have a data point X of I, it matches with my F, which map to my sensor S of I. So in other words, every sensor location should map out to what its actual state space measurement is. And I want to learn a map that does this. And I want to find the best F that does this. Okay, so that's the optimization framework we want to do. We want to learn how to take sensor measurements to full state measurements. That's the objective of the sensor problem. So let's talk first about, let's start simply, and let's talk about linear maps. Because linear maps is, you know, that's kind of our generic starting point. So in a linear map, this is how you might formulate this. We're going to use the SVD here because the SVD has the low rank structure. We're going to take our data matrix X and we're going to do a rank K approximation of the data. So you can do a singular value decomposition of that data matrix, and there it is. It's right on the top left, phi sigma v star. So phi itself are the dominant spatial features of the data, okay? And so what I would like to do is use those as a way to start placing sensors. So suppose I have some linear measurements H, so just look here, S is equal to HX. And X itself, though, can be approximated in a low-rank subspace by its projection onto those SVD modes. So in other words, phi nu. So nu tells me the projection of the X onto this low-rank subspace. And so the idea here then is you just optimize or least square fit of how do I determine what the best how to best do this. Well, there's your optimization routine right on the bottom there. You take, I want to match my signal to this measurement H projected onto the basis. And how do I do this projection? Well, like that's what I'm minimizing over, over that nu. Okay, so nu, the solution to it, is given by a least square fit. So what this is telling me is exactly how these measurements relate back to the original state space. Okay, in other words, how do I estimate from sensors an approximation to the full state space, which is on the bottom there, x hat is equal to psi times nu, and nu is what I just found through optimization, or at least in this case, since it's linear, least square fitting. Okay, so that's a linear map. And again, this is something that's commonly used for people because SVD is very easy to generate. You can do an SVD of any matrix, and you're taking advantage of subspaces that are usually linear subspaces that are typically interpretable in the context of which they were generated. Okay? The interesting thing about that whole thing is we can also then talk about sensor placement. Before I just said, here's your sensors. Now I want to talk about, you know, instead of, you know, here's where I place the sensors. Now I want to talk about like, yeah, but where should I put sensors? Right? I mean, that's a big question to ask is, in this formulation, I just put sensors down, but I didn't tell you where I put them. So maybe I put them in terrible locations. So wherever I put them, I tell you how to do the best you can with where I put them. But really what I should be determining is, where should I put them in the first place? So my optimization problem has to take into account the fact that I should figure out where is the best place to measure my system. So what we're going to do is start talking about optimal placement. And so we're going to do is basically start placing them based upon these QR pivots. It's a greedy algorithm that just simply takes the data, looks for the points with the highest variance and says, you know, the points with the highest variance, that's exactly where I should place sensors, because there's a lot of information there. And so what I'm showing you here is a couple things. On the top row, if I take that sea surface temperature data, if I use this QR algorithm with 100 sensors, 200 sensors, or 300 sensors, you can see how the sensors get placed. There's a structure to how they're being placed. So for instance, look at the 300 sensors. Do you see that bunch of sensors that get placed off of Peru, Ecuador there? This is basically the El Nino. Those sensors are there to pick up El Nino. Okay? Versus if you do random sensor placement, they're just randomly placed everywhere, which is what I originally said. You just place them somewhere and see how you do. That's what they look like. But here's the performance difference. Okay? So on the top is sort of the truth. These are low rank reconstructions of the sea surface temperature data with 100 modes, 200, or 302 modes. Okay? So that's kind of what let's call it the truth. And then what you're seeing below there are different strategies of sensor placement and how well do they approximate the truth. So on the top row in the middle is the QR algorithm. And notice with 100 sensors, you compare it to the above picture, and 100, 200, and 300, it actually does a pretty good job of getting a lot of the structure that you know is there from the truth metrics. This is just by greedy sampling, right? Greedy algorithm. Who has the most variance? Place the sensors there. Reconstruct the global state space with the SVD. If you use random sensors, that's the middle row, you can see it doesn't do well at all. And then if you do this compressive sensing trick, so you really use the compressive sensing idea, and it does terrible too. This is partly why nobody really does compressive sensing anymore. I mean, it just doesn't do that well, actually. So this tells you that like you have now a principled way to place sensors, and if I only give you 100 sensors and you really want to do a good job, you're going to use that QR algorithm. Okay, you can also modify this, and this is an important modification. What happens if it costs me money to place sensors? Right? That's a very important consideration if you're going to measure the ocean. Putting a sensor in the middle of the ocean is very expensive. Putting one on Ipanema, maybe not so much, right? I mean, that's the kind of thing you want to do. And if you tell someone who's got some money, and it's like, where should I place sensors? It's a lot easier for them to do this if they can place sensors on shore than out in the middle of the ocean. So we're going to now modify this greedy selection to include a cost function. And the cost function is going to be some kind of cost landscape we come up with that we're going to respect in terms of placing sensors. So for instance, here's the example. We're going to just make up a rule and say our cost function is we'll start increasing the penalty for putting sensors in the ocean. So on the top left, there's no penalties. We're going to put 300 sensors down. And on the top left, we basically just put sensors anywhere. Cost is no object. We can just place them whenever we want, and there they are. So you can see there's a bunch of sensors in the middle of the ocean. And then we say, yeah, but it's very expensive, so let's like penalize it. So if you penalize it some, you still have a lot of the sensors move to shore, some still stay out in the ocean, and then you even penalize it more, and then you get the bottom, the picture with the gamma is 225 there. You've moved all the sensors to shore. And then the real question is, if you look at those two panels on the left, where you have a bunch of sensors in the ocean, and all the sensors move to shore, what's the performance difference, right? Because this algorithm couldn't place sensors where it wanted. You made it constrain itself to be cheap, right? And the difference is right on the bottom. The true image is on the left, right? The bottom left. And the two images on the bottom is there's an error of 2.5%. That's the top left picture with you can place sensors anywhere. The 3.3% error is when you've placed all the sensors on land. So in other words, you saved yourself a bunch of money by moving all your sensors to land, and you only lost 0.8% in performance. That's pretty remarkable, right? That's the kind of thing that you want to understand if you're going to come to a real system. I saved you a bunch of money. Yes, you lost a little performance, but only not even 1%. But I saved you millions of dollars, right? Because you didn't have to go out in the ocean and try to place sensors. Okay? That's the kind of thing you can start doing when you want to start thinking about sensors and placing sensors. All that was based upon linear maps, linear mapping between the measurement space to the state space. And of course, I'm going to bring neural networks back up, right? So you could imagine I wasn't going to leave that one. Because what neural networks are is just basically, oh, nonlinear maps. So where the SVD is going to give you a linear map, neural network is just going to give you a very nice way to construct nonlinear maps. And so we're going to do exactly what we just did, except for now we're going to say, instead of this SVD playing the role here of mapping myself from sensors to state space, I'll just build a neural network to do it. Now, the nice thing is that these neural networks, again, have a lot of flexibility. They're compositional in nature. So like they take one layer to the next, to the next, to the next. They have a compositional structure. And they have this nice universal approximation theorems to go along with them. And so this is going to allow us to be a little bit more flexible than the very brittle linear map. But the linear mapping is great too, right? The linear mapping did a pretty good job, super easy to execute. But now let's see what a nonlinear map can do for us. And in particular, what we're going to do is now, remember we talked about autoencoders before, but now this really is structured to do decoder structure. So what I mean by a decoder, you're trying to build a map from the measurement sensor space, which is S, to the high dimensional state space X. So you notice in the middle there, it's a decoder. You start with measurements and go to the state space. And so what you need here is a set of training data to do this. And so what we're going to do is the input layers on the left, we're going to do just a couple hidden layers. And we're going to do a very shallow, we call this a shallow decoder because this is not a deep neural net. This is very shallow. It's basically a big pipe out to the data. And what I'm showing you on the left and the right of the network is exactly what we're doing. So on the left, you see those orange balls on the, we're going to do flow around the cylinder. You see where the orange balls are on there? Those are my sensors. I have 5 of them. And they have some numbers. So as I record in time, those sensors have numbers, right? It's like, here's what the sensor says. There's 5 of them. And at the same time that I measure those, on the right is what the flow physics looks like. That's what the state space looks like. So to train this neural network, I need pairs of data. I need, here's the full state, here's the measurements, and let's train a map between them. Okay? So that's what we're going to do, is we're going to take this neural net, we're going to train a map. So we're going to do 2 layers. Again, this is all this compositional structure that you have here. And again, this is just not that hard to do in TensorFlow, actually. So you could take something like TensorFlow, PyTorch. A lot of these make it really easy to do. All right, activation functions of the neural network. You can consider different things that people use, ReLU, Swish, soft shrinkage, whatever, who cares? Turns out ReLU will work perfectly well for us, so we'll do that. So the question is, what does it learn? So first of all, I want to highlight something very interesting here. The difference of what it learns from a linear to a nonlinear map. So the snapshots are up there on the left. This is flow around the cylinder. So it's got this von Karman vortex shedding going on. There's my decoder structure. And the question is, when I take that von Karman vortex shedding, those snapshots of this thing, and I look at the SVD modes, in other words, I do a singular value decomposition. I just look at the dominant mode structures. There they are in the top row. Okay? And what these modes are doing is oscillating in time to produce what looks like that von Karman vortex shedding motion. Okay? But notice something interesting. The modes there are all symmetric or anti-symmetric across the top and the bottom of the cylinder, which is interesting, right? So it's sort of, it takes this data, and because there actually is no, it does have that symmetry, right? Over time, you know, you could turn the cylinder upside down and it would look the same from the top and the bottom in some ways. And so you see that symmetry borne out there. However, if you take the decoder structure and you learn the mapping and you say, what do the modes of the decoder look like? They look like what they are in the bottom there. This is the nonlinear modes that you would learn from this. Now notice a couple things. Notice that the modes now look more like the flow physics, right? They look like the von Karman vortex shedding, right? I don't have to glue a couple of them together in my head. If they oscillate against each other, maybe I see that von Karman vortex shedding, which you have to do with the linear modes. The nonlinear modes have the structure of the flow field. So it's very nice. They give you a very different representation and interpretation of the mode structures. And that's what we're going to use to reconstruct the physics. Because, right, remember, this is this is about taking measurements and mapping them to the flow field. And in fact, you can show that you get a really pretty significant improvement in performance in comparison to linear structures, which is the true spectrum is the black. This shallow decoder is the red. So notice it just sticks onto the black for a long, long ways, right? Whereas the linear map falls off very quickly. In fact, the number of singular values is like, you know, you fall off after 5 or 6 singular values, then it just doesn't do a very good job. So whereas you get this right spectrum if you use this shallow decoder. Here's the other thing. So here's I guess in some sense the result of this. What you're seeing on the top left, you see where the orange dots are? I give you measurements there. What the actual flow field looks like is to the right of it, but you don't see that. What you have to do is figure out, can I reconstruct that from the measurements at those orange balls? So if you do a linear map, That's the top right. The linear map says, okay, if you give me these measurements of the balls, that's what I'm going to give you there, which is that top right, which actually doesn't look like the flow physics very much, right? It's pretty messed up. In fairness, it does have some of the structure of this, but it's a terrible representation of a specific instance of time of what this thing's looking like. There are some ways to improve this linear map, and that's on the bottom left, but still doesn't do that well. But the shallow decoder is in the bottom right. And look how well it does. By the way, the amazing thing is, you see on the top left, you see that pepper? We put noise on this thing. So we have noisy data. The shallow decoder not only gets it right, it also denoises it for you. So there's something to be said about nonlinearity playing a role in this space, because now these nonlinear modes offer you a lot of flexibility. Noise is just additive, but here in the nonlinear system, noise just gets shredded. It's out of the system. So that's very nice. These are just comparisons of the method, just showing that such a structure can really work pretty well for you. And again, here's a result from the shallow decoder. You see those black dots? Those are your measurements. And I don't remember how many we have, like 40 or 50 or something like that. And your reconstruction of the entire ocean is on the right. And you can just see that, like, you compare the two and it's like, it pretty much got it, right? So the shallow decoder does a really nice job for such physics. And this really can play a role in things like super resolution analysis. So this one's kind of remarkable. I give you a set of data. So what you're seeing on the left is from the Johns Hopkins turbulence database. So they've done a lot of high fidelity simulation. So this is some turbulent flow field. What is in the middle is a massively low resolution version of what's on the left. In other words, I'm going to give you a bunch of pairs of data, which is high resolution, low resolution. And by the way, the low resolution, it's not clear you can tell at all from that low resolution picture that the thing on the left is what generated it, right? It's pretty coarse. Hopefully you guys agree with that. But what you can do is say, all right, tell you what, let's make a map. Let's take a map from that low resolution picture to the high resolution picture. And I have a bunch of training data to do this, right? So I give you a bunch of low resolution images corresponding to a bunch of high resolution images. I train this shallow decoder, and then I ask the question, give me a new picture, a low resolution picture, and tell me what it looks like at high res. And that's exactly what it does. So in other words, the shallow decoder, after training, takes that low resolution images and produces the thing on the right. Which, I don't know, it's kind of, sometimes you have to just step back and understand that math is sort of miraculous, right? I mean, it all makes sense, but it's like, it actually works, right? Pictures like this, I think, are incredible. And that's the kind of thing that I think is so fantastic about using some of these data methods and some of these machine learning techniques, because they're just, they're just really remarkable. So I guess the conclusions of this piece, and I'll finish with some concluding comments overall, is that, you know, there are a lot of different things you can start thinking about, and measurement is something you definitely want to think about. Measurements, you can think about linear measurements, and linear measurements are really nice in the sense that there's very fast, greedy algorithms like the QR pivoting. And also you can put cost constraints, all these things that are easy to handle in linear frameworks very nicely. However, nonlinear measurements offer you some really interesting perspectives on this, including, you know, in some sense, improved interpretability, which is kind of interesting. Usually you don't use the word interpretability with neural nets, right? You say like, well, I wish it was more interpretable. In this case, it gave us very interpretable things. It gave us more robustness to noise. It gave us the ability to do super resolution. And also because it's a shallow decoder, we could get away with a lot less data than if you're trying to train like some deep neural net, okay? So these are just things to think about when you go to real data and how to start thinking about building all this into your discovery pipeline. Because remember, with this data, you could then go and bring this data into some of the other architectures we talked about, which is like, okay, can I train an auto encoder now, plus a neural net to do SINDY, right? These are the kind of things you can do within this structure. And I want to finish with this graph here. So I feel like I covered a lot of things for us, right? I talked about DMD, Koopman, SINDY, neural nets. And the question is, when should you use any of these? When should you not use some of these? And what I tried to put on here are some concepts you want to think about. And in particular, this axes that I have here are 3 axes that you really need to think about at some point, which is on one axis is the quantity of data. In particular, if you don't have a lot of data, you're not going to train a neural net. Okay, so can we just put that right on the table up front? If you don't have a lot of data, you probably shouldn't be training a neural net. Okay, so before you take off and start saying, I'll just do a neural net for this, just ask, how much data do I actually have? If you don't have enough data, don't train a neural net. Neural nets have been around for a long time, by the way, since the 90s. And the reason they didn't take off in the late 80s and early 90s is we didn't have enough data. And that was proven to us in 2014 with the ImageNet data set, which had 15 million labeled images. And then people realized, oh, that's the kind of data you need to train deep neural nets. So quantity really matters a lot. On the z-axis there, noise. How good's your data? What's the quality? A lot of really good models don't handle noise very well. DMD, you can always get a DMD model. It might not be that good, but you can always get a DMD model. Whereas if you have a significant amount of noise, or you know, all of those methods like neural nets, SINDY, Koopman, they're all going to break. Okay, and then also observability. What I mean by observability is you measure a portion of your state space. How well can you build models with it? Again, the more observable it is, the better your potential for building good models. So one way to think about it is that if you have low noise, lots of data, and lots of observability, neural nets might be a perfect way to handle the whole thing. But also SINDY, Koopman, all these things. So you get to pick a method, and you also get to pick if you want this thing to be interpretable or not, right? And so this is just some kind of rough sketch of ways to think about things, allowing you to make some decisions about what methods you should be using. I'll stop there. It's almost 5 till the hour, but can take questions. So I guess I open the floor for that.
Thank you. Very, very interesting. I guess we have a lot to talk about. And okay, let's see if someone else, Americo or
Nathan?
Yes.
Yes.
In these randomized algorithms, in some sense, you want the smallest initial sample as possible, but of course can't be so small. You need to cover a significant part of the space so that you can reconstruct. But this is the point. How much of the original space is necessary to cover in order to invert the map and you recover the original, or a good approximation for the original image signal? Because I can pick a very small set, but suppose you have a megapixel image and you pick only the first line. It's a very tiny part of it, but totally non-informative. How to distribute that sparse sampling that you needed to sample your original signal, matrix, image, whatever else.
Yeah, so a lot of times so there are some theorems around this, by the way. So oftentimes what people like Kendez and Donahoe, when they did the compressive sensing, they were thinking about it from the point of view of image reconstruction. And so they were thinking a bit about pixel space. And in that case, you would say, if I have an n-dimensional state space, which n is large, and the idea was if there is some R rank object in there, in other words, where R is really sort of some low rank structure. So R is much, much, much less than n.
Mm-hmm.
Then what they have is a theorem for how many samples K you need to appropriately randomly sample to reconstruct that R-dimensional subspace. And there's K is equal to something like R log of R, what is it? R over, and I can't remember the formula off the top of my head. So basically you have to randomly sample more than the rank of that subspace, right? Suppose that subspace is 20 degrees. You might sample it like, okay, then 40 random locations.
But may I sample according to any probabilistic law? I can choose Gaussian, uniform, but
they usually,
if I pick a more biased distribution, some distribution which has more mass to one side of the domain than the other, this will work too.
I mean, I would pick that depending upon what you know about the data. So for the examples where they've derived these theorems, there was no bias. They just did Gaussian random sampling because there was no structure to the data. Now, if you have data and you understand there is structure in your data, like all the important stuff is happening in the middle, sample in the middle more. You know, in other words, bias your sampling towards where there is actual structure. And in fact, that's the one difference between the compressive sensing, I would say, and something like the QR. The QR is trying to sample where stuff is happening. It's not just random sampling. It says, well, first of all, tell me about your data, and where there's a lot of variability, that's where I want to put my sensors. So it's smarter than random sampling, although oftentimes for the image processing, they just say, look, images are images. Let's just randomly sample much more than the intrinsic rank and we'll be fine. They don't care about point measurements. In physics, we care about point measurements. You know, they don't care if they use 10 times more than they needed to, but if you're putting down sensors in paying form, you do care about putting down 10 times more sensors, right? You care about, I want the absolute minimum number of sensors if I can get away with it. So then you bias where you place these.
Another question, now curiosity, about that randomized SVD you presented in the beginning. Suppose I'm not interested in compressed information, but I need to solve a huge linear system so that even I can, maybe I don't have memory in my computer to store the matrix. How accurate is the solution obtained for this linear system obtained by this randomized SVD?
It actually can be very accurate. I mean, you know, part of it is part of the theorems that go with this. I mean, there are theorems around exactly how accurate it is, but a lot of these theorems are making some kind of assumption about there being some R rank subspace, right? So if you have data that really has sort of some low dimensional R rank, low dimensional subspace, it's going to actually do a great job in constructing your solution, because that's the space where everything matters. And that's exactly what the randomized SVD is getting after, is let me approximate that space. And in fact, it does a very good job of converging into that space, even if you're just doing randomized sampling, so that you can solve in that space.
So this may be a solution for real-time processing, maybe. Sometimes you can't, you need, I'm thinking control.
Yeah.
I'm trying to develop a control plant where I need to solve a linear system, but this is the bottleneck. It's slow for the original dimensions, but maybe using this randomized version, I can speed up this.
Yeah.
Without
and in fact,
accuracy.
that's one of the things that we advocate for a lot is pretty much any really large scale system, you should just be using randomized linear algebra up front. That's my
Fantastic.
personal opinion. And because if you're going to do real-time stuff, it's just absolutely necessary to have something like this.
Mm-hmm. Absolutely. Nathan, thank you very much. Fantastic course.
Thank you, Minicourse.
I'm sorry for interrupting you many times.
Oh, no, that's fine. I'm glad. Otherwise, I would have been, and I'd run out of things to talk about.
Okay, so any other question out of America? So I think that people have a lot to think about it. You have a lot of, you know, the brain cell or.
Hey, let me just share one final thing, and hopefully, you know, hope nobody takes this wrong, because usually it seems a little bit self-serving, but I hope it's okay. So if you go to my website, on the very far right, there's a link to open source lectures. And I have all kinds of materials there. In fact, you can download the PDF for all these books. There's all kinds of YouTube lectures. There's all the code for these books. Everything I talked about here is much more in detail here and has a lot more depth with code, with everything. Just like I said, go to my website, copy my open source resource lectures, hit there, and then I have a bunch of courses, a bunch of materials. Like for instance, this book here on data-driven science and engineering. Every section of the book, we have YouTube videos to go along with it with code. And in my videos, I tell you, and here's the PDF to the book. So the point is, everything here is super easy to access. It's all on YouTube. And you know, part of what we've been trying to do is make everything open source, code, books, lectures, everything. So just something to be aware of if you want to follow up further. There you have resources available to you if you want to follow up that.
Great. I'm sure if many people already have the books, but the other they don't have, they will have soon.
Yeah, I have the three. They are excellent.
So thank you so much, Nathan. And then I want to make an announcement, because actually we are going to have Guy Caputo from Rennes on Thursday, but then next week we'll have Pedro Maya. So again, talking about neural networks. So I'm sure related topic to Nathan. Okay, so I'll, well,
okay.
I'll see you again. Okay.
See you guys. Thank you so much.
Thank you very much, Nathan.
Okay. Bon touch.
Bye-bye.
Ciao.
Ciao, ciao.